Hello students, in this video I will be giving you an introduction to the concept of annuity. An annuity is a series of equal payments made at regular interval of times. So we're going to be thinking in money, and if we are thinking in money, we need to be thinking also in times. Time and money go together. So thinking a time as a line, then an annuity will be a series of payments. You are making payments, I'm going to call it with the letter R, and these payments are not only equal but also are made at regular interval of times. This time could be every month, for example. So if we have this set of payments, all of them of equal size, and they are made at regular intervals, so the time between two different payments is always the same, then we have an annuity. So you can be thinking, for example, you are saving money and you are putting the same amount of money at the end of every month, for example. This will be an annuity. Or, for example, if you have a loan and you are paying this loan at the end of every quarter or at the end of every month or at the end of every year, you are having an annuity. So when you're paying a loan and if you pay the same amount every time, you have an annuity. There are several quantities involved in an annuity. And the first, of course, is the payment. And the payment will be symbolized by the letter R. Another important quantity will be the number of payments. So you can count how many payments you made. And for this number of payments, we'll have a symbol. We are going to be using the letter N. Another important quantity, it will be the time between two payments. That is called the payment period. And usually, in any annuity, this payment period could be a month or could be a quarter. So we say that the time between two consecutive payments could be monthly, could be quarterly, could be semi-annual, or could be annual. So you are making payments every year. At the same time, there will be another period that is important, and is the period of conversion of the interest. Because this is money, there are interests involved here. And this is called the conversion period. And again, this could be monthly, quarterly, semi-annually, or annually. It could be also payments that are bi-weekly or weekly, but these are the most common. And these are also conversion periods that are weekly or even daily, but these are the most common: monthly, quarterly, semi-annually, or annually. Another important quantity is the term of the annuity. The term of the annuity will be the time between the beginning of the first payment interval and the end of the last payment interval. So this time is symbolized with the letter T, and you can be thinking that is all this length of time between the beginning of this period to the end of the last period, of the last payment period. The payment could be made at the end of each period or could be made at the beginning of each period. For example, when paying the rent of an apartment, usually you pay at the beginning of every month. So in this case, you are not paying at the end, but you are paying at the beginning. So there are two types of annuities. Annuity when the payments are at the end, and annuities when the payments are at the beginning of each payment interval. So depending on this, we divide annuities in type of annuities. So the first one is the ordinary annuity, when the payments are made at the end of each payment interval. This type of annuities looks like this. If you think in the time as a line, then the first payment is made at the end of the first payment interval, and the last payment is made at the end of the last payment interval. Opposite to that, we have what is called the annuity due. And an annuity due is one when the payments are made at the beginning of each payment interval. So they look like this. The first payment is made at the beginning of the first payment interval, and the last payment is made at the beginning of the last payment interval. Anyway, the time between two payments is the same. These two types of annuities, both of them can be classified in something that is called simple annuities. And a simple annuities is an annuity when the payment period is the same of a conversion period. For example, we are making payments every month and the money is earning interest monthly, so this will be a simple annuity. Or you make payment every quarter, every 3 months, and the interest is compounded quarterly also, then we have a simple annuity. Opposite to this, we have what we call a general annuity, when the payment period is different to the conversion period. That happens, for example, in Canada, when you are paying the mortgage every month, but the interest in the mortgage compounds semi-annually. So the payment period is a month and the conversion period is semi-annual. So in this case, we have a general annuity. Obviously, an annuity could be ordinary and simple annuity, or could be ordinary and general annuity. In this video, we focus in the annuity that are ordinary annuity and also simple annuity. So the payments are made at the end of each payment period, and the payment period is equal to the conversion period. So we call this type of annuity ordinary simple annuities. They are ordinary and they are also simple. There are other concepts obviously involved in an annuity, other quantities. One of them is what we call future value. Let's speak about this future value. And because in this video we are focusing in ordinary simple annuity, we are going to see how to compute the future value of an ordinary simple annuity. But let's speak first, what is the future value? Assume that we have an annuity, so we have a series of payments of equal size made at regular interval of times. And we know how many payments. We know that there are n payments here in this annuity. So the future value of the annuity will be the value of annuity at the end of the last payment period. So what we are going to do to compute the future value is use this point as a focal date, use the last moment of the last payment interval to compute the value of all these payments. So that will be the future value. We can say that the future value is the equivalent value of all the payments made in the annuity, when the focal date is the last moment of the last payment interval. So what we need to do is compute the value of all these payments in that date and add together all these values to compute the future value of the annuity. And I'm going to use this symbol S sub n. We have n payment, will be the value of this last payment, and the value of this last payment is R. So I'm going to type R, plus the value of the previous payment that is made one payment interval before the focal date. So it will be plus R1 plus I to the power 1. And obviously there will be another payment that is made two payments interval before this R. The value of this payment will be R1 plus I to the power 2. And we can continue finding the value of each of these payments until we get the value of the last payment. The value of each of the payments that focal date will be R multiplied by 1 plus I, this I is the periodic rate of interest, to the power the number of periods that are between the payment and the focal date. The last one actually is the first payment of the annuity. So the value of the first payment of the annuity will be R multiplied by 1 plus I to the power the number of payments between this R to this focal date. And you notice, because there are n payment periods, the exponent corresponding to the first payment will be n minus 1. So it will be the number of periods minus this one that is here. Until that point, we are going to finish the sum of all the values of the payment. So we continue the same way until we get the value of the first payment in the annuity. The value of this payment will be R multiplied by 1 plus I to the power n minus 1, because there are n minus 1 payments between this R and the focal date. So if you add together all this value, that will give you the future value of the annuity. So obviously, it will be a hard work if we compute the future value of the annuity in this way. So it will be a better idea to look for a formula that can simplify this long sum. That could be a very long sum, especially if we have too many payments. You notice that this R is a common factor, so you can type R, open bracket, that multiply 1, because this R is multiplying 1, this R is multiplying 1 plus I, this R here is multiplying 1 plus I squared, etc. So you can open bracket, and this will be the sum inside the bracket. So if you have a formula for simplify this, you will have a formula for the future value of an annuity. If you see this, maybe you can recognize that this is one factor or one factoring case. When you are factoring the difference of the same power of two quantities, you have this formula, the difference of the two quantities, multiplied by this factor that have terms when the first quantity appears with some exponents that go down. So the first exponent is n minus 1, the second exponent n minus 2, etc. And the exponent of the second quantity go up. For example, here b is to the power 0 in the first term, the second term is b to the power 1, etc. And the exponent of b go up until the last. If you remember that, maybe you can recognize that it looks like this, especially if this a is number 1. Let's put here 1, and you will notice that it's exactly the same of this. For example, if a is 1, this will be 1 minus b. Here will be 1 plus 1 to the whatever power is 1, so the second term will be b. The third term will be b squared, because this a to the power n minus 3 is 1. So this will be b squared, etc. until the last term that will be bn minus 1. So you can think in this way better. 1 minus b to the power n equal 1 minus b, 1 plus b1, b2. So see this, and you will notice that will be very similar to this. If you want to know what is the value of this factor here, that have all this power of b, the sum of all this power of b, you just need to divide the expression by 1 minus b. So the factor whose terms are all this power of b will be 1 minus b to the n divided by 1 minus b. Or you can change the sign and say that this is b to the n minus 1 divided by b minus 1. See that I have multiplied by minus 1 both of the numerator and denominator of this expression. So we have an expression for the sum of the powers of b. In our formula of the future value, this b will be 1 plus I. We are going to have that Sn will be r multiplied by b to the power n, but this b is 1 plus I to the power n, minus 1 divided by 1 plus I minus 1. Remember, in our case, this b is 1 plus I. So open bracket, and you have 1 plus I to the power n minus 1 divided by 1 plus I minus 1. This 1 cancels. Sn will be r 1 plus I to the power n minus 1 divided by I. And you have an expression for the future value of the annuity. Sometimes in some textbook is written in this way. So they use the symbol future value, FV, and for the payment, they use PMT. We need to learn the formula that we are going to use to compute the future value. So we're going to start from here. Anytime that we're going to compute the future value of an ordinary simple annuity. This N is the number of payment periods, so actually the number of payments. This I is the periodic rate of interest, the interest in every period of time. And this R is the amount of the payment. If you substitute this value in this formula, you are going to find the future value. There will be some situation when this future value is important. This situation will be when you are accumulating money. For example, if you are saving money. If you have a saving account and you are making payments of equal size in regular interval of times, you will be interested in what will be your accumulated value at the end of these payments. you have an RRSP, for example. This is a case of a saving account. This is a registered retirement saving plan. You're making equal payments in regular period of times. Okay, in this case you will be interested in computing the future value. Let's solve some examples of this. What will deposit of $60 made at the end of each month amount after 6 years if interest is 4.8 compounded monthly, for example? So in this case, we have an annuity like this. You are making payment of $60 at the end of every month, and that happened for a term of 6 years. What we know, for example, R, that is $60, so I mean, you know the payments. You know the nominal rate of interest, that is 4.8%, let's call it a small r, 4.8%. And you have also that is compounded monthly. So you know two things here, that the payments are made at the end of each month, or the payments are monthly, the payment period is a month, and the conversion period is also a month because the interest is compounded monthly. So this is a case, an ordinary annuity because the payments are at the end, and it's also a simple annuity because the payment interval is equal to the conversion interval. Both are monthly. And I'm going to use the letter M to symbolize how many payments per year. Obviously, it's also how many conversion periods per year in this case, because both are the same, the payment period and the conversion period. If we know this nominal rate of interest, we also know the periodic rate of interest, because it will be, the periodic rate of interest I will be 0.048 divided by 12. Okay, so we have this periodic rate of interest, and we also know that the term is 6 years. So we can compute the number of payments. So the number of payments will be these 6 years multiplied by this 12. 6 times 12 equals 72. So we know everything to put into the formula. So let's do it. The future value Sn will be, this is the formula, Sn equal R multiplied by 1 plus I to the power n minus 1 divided by I. So that gives me Sn equal 60, open bracket, 1 plus 0.048 over 12 to the power 72 minus 1. And divided by I, that is 0.048 divided by 12 again. You can use a calculator for doing that. And obviously, I'm going to be showing you how to use a scientific calculator for doing that. I'm going to bring this calculator, the Sharp 520 TG. Yeah. So, what to do? I get my calculator and I type 60, then I open the bracket. So this is the bracket of my calculator, so I click here on this bracket. Just for you to follow easier, whatever key I'm pressing here, you're gonna see that appears here beside the calculator. And obviously in your calculator appears in the screen also. There is another bracket here, so open the other bracket. Then number 1, I press number 1. Then the key plus sign, so plus 0.048 divided by 12, so 0.048 divided by 12 divided by 12, 1, 2, and close the bracket. So I close the bracket, close one of the bracket to the power 72. This is the key power that I have in my calculator, y to the x. So to the power 72, 72. And then this minus 1, so minus 1, and appears another bracket. So I'm going to close this bracket. So, and after this bracket, type divided by. So use the key divided by. Anytime that you have an operation at the denominator, you can put it in brackets. So divided by open bracket, 0.048, 0.048 divided by 12, and close the bracket of your denominator. So I close the bracket. Now press equal signs and I give you the answer. 4,994.869837. you can round it to two decimal, 4,994.87. So we can think that the deposit will amount to 4,994.87 at the end of the annuity. So that will be the future value of the annuity. So let's see another example. Mrs. Jagger made ordinary annuity payment of $15 per month for 16 years, earning 4.5% compounded monthly. How much interest is included in the future value of the annuity? Oh, in this case, they are asking me how much interest. But we can compute the future value and then subtract the value of the contribution of Mrs. Jagger. And that will give you the interest. So you have an annuity like this, when your payments are $15, and that happened during 16 years. So what do you know? You know that the payments are $15, that the nominal rate of interest is 4.5%, that there are 12 payments per year because the payments are monthly, and also the conversion period is monthly, so there are 12 conversion periods per year. This is a simple annuity. N will be the time multiplied by M. So 16 years multiplied by this 12. So to know how many payments in total will be 16 times 12, that is 192. This is the number that I'm going to use in the formula for the exponent of 1 plus I. So that will be N. So let's use it in the formula. So this will be 192, this R will be 15, and this I will be the periodic rate of interest will be this 4.5% divided by 12. Or better, 0.045 divided by 12. Let's make a substitution. Now that I made a substitution, use your calculator. Okay, 15, I type 1, 5. Open bracket, I open a bracket, I will open another bracket, 1 plus 1 plus 0.045 over 12.045 divided by 12, 1, 2, and then close the bracket to the power 192. So to the power 192. Minus 1, so minus 1, and I close the bracket. So what I do in my calculator is just type exactly what is written in the formula. Type in the formula in the calculator. Everything divided by, and this just take into account that the denominator needs to be written in brackets. So it will be divided by, open bracket, 0.045 divided by 12, divided by 12, and don't forget to close the bracket of the denominator. Press equal signs, and that gives you the answer, 4,206.67 rounded to two decimal. So we have then that this is the future value of the annuity. How I compute the interest? Okay, the interest will be equal to this future value minus the contribution that you have actually made, or Mrs. Jagger has made. What is the contribution that Mr. Jagger has made? The number, the payments multiplied by the number of payments. So, Mrs. Jagger has made 192 payments of $15. So this will be then, Sn is 4,206 minus N times R, the number of payments multiplied by the payments. This is the actual contribution. So it will be 4,206.67 minus 192 times 15. This 192 times 15 is the actual contribution of Mrs. Jagger. If you make this subtraction, you're going to get the interest that Mrs. Jagger has earned by saving this money in this way. So that will be $1,326.67 will be the interest. Okay, with this I finished this problem, and I finished my explanation of this part of computing the future value of an ordinary simple annuity. In upcoming videos, I will be showing you how to solve problems in which there is a combination of an annuity with a period of time when there are no payments, in a period of time when only the compound interest is working. For now, let's stop here. I hope that you have found this useful. Thank you.